a pleasure to be invited along. So let me introduce myself. I'm Stephen McArthur from University of Strathclyde, and I'm going to be chatting about energy security. And I'm going to be thinking about it from the perspective of how we're leveraging data, AI, and self-organisation for that as well. And actually, I think it's excellent placement, Jeremy, because I think there are some themes that Peter's just spoken about that come out on what I'm talking about as well that might lead to some interesting conversations. But if you let me just move through a little bit, let me give a bit of context. We're all aware of the enormous change that's going on around energy and the drive towards net zero. And taking just even a UK perspective, we can see how quickly things have been moving from signing up the net zero emissions law back in 2019, creating these targets. We've got the COP conference going on just now. Governments have got their net zero strategies. The UK one is here. And it's really all about decarbonising the energy system and making sure that we move to a point where we have security of supply, we have decarbonisation, and we protect the planet going forward. And to do that, there is a lot of work and a lot of rapid change required. And what I want to talk about this evening is about some of the research, some of the work we need to do around making that a feasible journey, and making sure that you understand the type of things that I'm interested in around AI and what that can play into that area. So we're seeing some massive changes, which I'm going to talk about, but we're also seeing things at different scales. So in some respects, if you look in some countries, there's some large-scale changes of energy systems. So moving away from coal-fired, perhaps nuclear, perhaps not nuclear, wholesale growth of offshore and onshore wind energy, rollout of photovoltaics, massive changes in the generation technology. Also, people are thinking closely about the individual and the local. So those other technologies I talked about there are about massive scale, but we're also seeing more and more people thinking about what happens in communities, what happens at the local level. And there's a major programme going on in the UK at the moment called Prospering from the Energy Revolution, which is £102 million, looking at what local smart places might be like in terms of energy, and how we as individuals might start to engage with that energy system more, and how local markets and local generation and balancing of local generation, local demand and local markets might help the national. So you start to get this energy system that you're having to think about at different levels and different scales, and each part has to interact with each other for the overall benefit of our energy security and to deliver our decarbonisation journey. And then if you think about what that means is this, that everything's changing rapidly. As I said, offshore and onshore wind farms, increased use of solar, distribution connected generation. So that means lower and lower down the electricity network. Further down it, you're actually getting generation connected where you didn't used to have it at street level. You know, you might have photovoltaics on the roof. You might have electric vehicles that eventually are batteries that charge, but also give energy out when needed. And then you're starting to see storage. And the electrification of our infrastructure is accelerating. So in the UK, we're trying to move away from gas heat and gas powered to electrification of heat and electrification of transport. And then when you add into all that, you've got other things such as hydrogen and heat networks. So the message for me in all of this is the operation, management and use of this energy network is going to become increasingly complex, and the complexity is going to become unmanageable in terms of the human control that we used to rely on. And therefore, we're needing a whole new approach and thought process about how we actually ensure we have this security of energy under this changing environment. It's a changing environment where we don't know what the endpoint's going to be because we're not fully architecting it yet, that we know the endpoint. There's evolution at each stage and rapid change. And in fact, in Europe, for example, the European Technology and Innovation Platforms Initiative have created various brochures, diagrams, and views and visions of what security might look like. Very busy diagram here, but I think the key thing is the fact that it's a system of systems. So you have hydrogen systems in there, you have gas, perhaps some that you're using to the point that you don't any longer have gas. You've got electricity, you've got transport, you've got vehicles with batteries producing energy into the grid, taking it out. You've got the telecommunications networks that's required to understand it. You've got offshore, you've got onshore. This systems of systems becomes enormously complex to try and manage and bring together. And that's where my research and interest in energy systems and interest in data, AI, and advances around data solutions comes together. And I think that's where it also resonates with Peter's idea around strengthening communities through AI. But we're talking about energy communities here, and also helping large organizations, because you'll have large infrastructure delivery organizations. You'll have network operators running electricity networks. You're having to serve those and the needs of those, and they're trying to serve the large scale community. But you'll have local energy. In my home, I might have a photovoltaic on my roof, I might have a battery wall, and I might have an electric vehicle, and there's some local balancing and services I can provide. So you're dealing with the national level and the local level that have to interact together. And that drives this need for smart. And I think for me, what we need to be doing in this energy security space is thinking about what the real needs and opportunities are and why smart needs to be used. So it's not about using AI for the sake of it. It's not about using new smart technologies for the sake of it. It's about understanding what we need to achieve and how we can help that and move the system in that direction. The diagram that's on the screen at the moment is taken from the European Distribution System Operator Organisation, EDSO, and it's their sort of high-level view of bulk power production at power plant, but also that could be major wind as well, transmission for bulk transfer of energy, and then in bulk transfer of power down to distribution systems, where it then starts to get more local and right down to the local level. And if you think about at each of these levels, the need for smart, at the transmission level, which is the highway for power transfer in large volumes, there's a huge increased complexity of maintaining security of supply there. You're getting a much more complex system that you've got to make sure is stable. We have to, what we just say is deal with reduced inertia. That's because we no longer have large power plants with rotating equipment. We've now got lots of wind farms with power electronics, which is a very different way of having equipment on the system, which means when something goes wrong and there's faults, you get a very different type of behavior around power systems issues in terms of frequency, voltage, and the traditional things that power systems and grid have had to solve. So you're having to change the speed and the approach that you deal with that. And you have to coordinate all of that with what's going on at the lower distribution level. You move down to the distribution level, then you're moving away from what was traditionally a distribution network operator, somebody that just ran the network and the power flowed from the inflow to the network down to the houses, homes, schools, communities and industries that it went to now you have a system that's got two-way flows, because we've got electric vehicles and photovoltaics pushing energy into the system and moving power around in different directions. And we now have a whole new set of problems around actively managing that network, making sure that we are within the limits of the power that the different equipment can handle. And we're starting to think about at that level, how do we balance smart local energy systems? How do we balance the use of hydrogen, electricity, existing gas? And then also have improved asset management and condition monitoring. And down at the local level, how do we have flexible energy markets where we can do peer-to-peer trading? So we have this completely different world of energy and complex interactions. But at the same time, we are needing to maintain security of supply and resilience of the energy network, because we do not want to move into the situation where people are going off supply. And most of the countries we live in, that has been the norm for many, many years, that we are guaranteed our supply and we very, very rarely see it interrupted. So we now need to be able to do that in this whole new environment. So one of the areas that I'm very active in and is very important as this is flexible, scalable and reusable control architectures. Because as you build these type of new energy systems, and if you think about smart local energy systems, as we think about that, throughout their life, what we've experienced in the energy system is there's constant upgrades in devices and protocols that are used for control, for management of those devices. There's digital and physical extensions. What I mean by that is you're adding new energy sources. Suddenly a new wind farm might be connected. Suddenly a new battery storage might be connected in 3 years' time, 4 years' time. What we've done in the past with the grid systems is extensively put copper in the ground and physical equipment. And anytime there's been a major change, there's been a significant cost to adapt. And there's that inherent inflexibility. We're having to move to a world now of real flexibility where you can adapt to those changes as easily and as quickly as possible. But we need scalability as well. So that means as we have these control systems, as we are managing when things are charged, when we are balancing out load with the generation supply, then we need to have easier and cheaper upgrades and updates on the system going forward, so that every time we adapt and change the energy system, it's not a very expensive refit. So we need that more flexible data and information approaches and easily adaptable control. And we want reusability. If we find a system that works well in one locale, we want to be able to move that. And that's always been a problem as well. And actually the sidebar diagram there is a research program I'm involved in called EnergyRev, the Energy Revolution Research Consortium. And that's 22 universities working around that program around smart local energy systems, actually trying to provide evidence for how you scale up smart local energy systems and how they sit inside existing energy networks and how they balance national and local behaviour. And one of the things, again, I think that resonates with what Peter was talking about previously, it's also about giving control and power on the energy system to consumers like you and I, so that we have the flexibility to do what we want with the type of energy system we want, what we want to do around our house, but it's done in such a way that it improves and supports the bigger network operation and the wider energy network. So we need new ways of bringing in self-organisation, of using data, of using AI to drive that. So with that as background, I thought I might drop into some examples of specifics that we've been working on and examples. So one of the things that myself and the team have been working with, and in this instance, there was a team that at that point was out of New York University that we were really interested in at this distribution network and low voltage network level, as you connect distributed generation, new generation into the network, which might be more renewable and supporting the network. The complexity of managing that network became more and more difficult. And within this New York network, you started to hit constraints. So bits of the network where you couldn't push any more power, or it became problematic for the equipment that it could damage it and cause problems. So what we needed to do, we also wanted to control the voltage and regulate the voltage in it, because that allows all the devices to operate correctly. So it's a complex problem. And New York University had come up with an approach of pre-calculating how that network could be broken down into smaller sub-networks that could be more easily managed within the constraints that were required. We took that and took it to the next stage and thought about how would you make this self-organising, so as things were connected, as faults happened, as behaviours changed, as the way the network was operating changed, could it dynamically reconfigure and come up with different compositions of sub-networks for control that would actually drive us towards that improved situation. So we used the epsilon decomposition approach, looking for when something happened in a network. It started with certain sub-networks. Using an agent-based approach, we had agents that were looking for network violations, things that went wrong, violation detection. And then if they detected something going wrong, they could communicate with the other agents and they could start to reorganize which ones were controlling which part of the network, which distributed generation was feeding into part of the network, switching the sub-network for control, and starting to adapt and change the different organization of assets and generation to get the correct behavior that you wanted and the correct electrical characteristics in that network, so that it was safe, resilient, and secure. So we've done a lot of activity around this and found that this is a very effective way of controlling the networks. And the bullet points here I won't go through in detail, but basically under a whole host of different case study scenarios where there is voltage problems in one part of the network, the control agents within that part of the network were able to solve it. And the diagram at the bottom shows the type of negotiation that goes on between them. So they negotiate to try and optimize the set points. The case study on the right hand side was when there was violations in multiple parts of the network, and it reorganized into different composition and different agents in the two different areas, negotiated with each other, and were able to come up with the correct set points. So what we were showing here was, in this big complex situation, you could actually have a form of self-organisation where, through negotiation and cooperation, you could manage the network and ensure you had security and resilience. So that's where we see self-organisation being required to manage these complex networks. The other part, I guess, that I was going to talk about was there's also a real drive around taking what's been going on in the whole AI and data world and working out how it really helps some of the major issues that we have within energy and energy security. So how do we tackle the right problems and use the correct techniques to do that? And some of the approaches to using data and AI that we've been looking at that feed into what the utilities and the network operators require are shown here. So one is building greater system intelligence for identifying environmental threats. So one of them is ice accretion on overhead lines. And this can be a problem in the UK, but in places like Canada, it can be an enormous problem because actually, from the weight of the ice, it can bring down whole transmission corridors, which has happened in the past. So we have been working on ways of using the data that's automatically generated in the networks to start to identify when this ice might be building up. And then you have ways you can deal with it. You can push for more power down to try and melt it. You can do other things. So we're trying to look at what's happening in the environment using data to work out aspects of that. One of the other things, the bottom right hand side of things, is also part of energy security, is identifying when there's going to be faults and dealing with them rapidly. And one of the issues we have is we know there's a lot of weather-related faults. For example, it can be a very warm part of the year. The ground dries up and cracks and is dry for a long period of time. And then if there's a heavy rainfall, the water seeps in, hits cables and causes cable faults. That takes customers off supply. So we've been working with a number of companies to look at, but in those parts of the network, they don't often have many sensors and a lot of data. So what we've been doing is working with previous historical data about where faults occur, mapping that to weather data, being able to build predictive models between weather conditions and where faults happen, and then use that predictively and linking it to weather forecasts, so you could forward forecast when there could be faults which could impact on energy security. And then the final thing on this slide on the bottom left-hand side is we've got this move towards electrification of heat and the use of heat pumps. But what we don't really know is what the big impact of those are going to be on the existing distribution network. So we've been trying to look at a way of working out what the penetration of heat pumps might be and what their use might be at different times of the day. And what we've been doing to do that is picking out heat data in terms of gas heating and behaviours with gas heating linked to weather, temperature, and then doing a mapping across to what that might mean for heat pump load and how heat pumps might be used, and then modelling what that impact would be at those times of day on the network to work out exactly what is going to happen in the network with heat pumps instead of the heat system we've got just now, and can the network manage it, or what type of self-organisation and improvement does it require. So across this energy security area, we can make use of data forecasting, self-organisation to try to combat the real complexity that we're seeing. And I'll just skip over the next one, I think, in the interest of time, and come to a conclusion. So what I've tried to outline there is, as part of energy security, in terms of leveraging data, AI, and self-organisation. And first of all, part of it, the bullet points on the left, is about heading towards much greater involvement of the individual. So we'll all be more involved in this energy system. Might have electric vehicles, might have heat pumps, may have other aspects that we have in our house, photovoltaics, battery stores, as I said. But actually, a lot of individuals don't want to have to manage that and make decisions about what set points they're at and when they use the battery versus the battery and electric vehicle versus the grid supply. So while there's much greater involvement of the individual, they want to devolve control And that's where a lot of this intelligence needs to come in. And it has to be balanced such that it's in the interest of the individual and the overall global use of the energy network. So I think that means we need to understand the application need and value of the data, the AI and the self-organisation with respect to energy security and resilience, work out what problems we're trying to solve and use the techniques towards it and build those appropriate AI and data systems. But when we do that, we need to ensure they're effective and they deploy and they can scale. Because one of the things is we've built many demonstrators of these types of technologies, but they're not necessarily that scalable. We need to make sure that the end user understands them, and it starts to go into some of the trustworthiness that Peter's interested in, and that they can also be transferred rapidly to similar issues. And also with the regulatory requirements. And then in overall this energy system with these technologies, we need flexibility and adaptability. Those are imperatives. We need flexibility for the system, so the system can change over time because we don't know what the end state point is going to be. But we also need it for the individual, because it needs to be flexible. The individual can change what they do, and it needs to be flexible for the future. And the diagram on the right-hand side is really the model that we're trying to use on linking with either consumers or companies of helping to set goals with the management and the people involved in the organisation and building the right systems with the correct algorithms, integration, human AI interaction and operational validation to show the correct journey towards energy security through data, AI and self-organisation. So hopefully that was interesting run through some of my views around energy security and where my work on data, AI and self-organisation techniques come into it.